In this problem, we have a chandelier of mass m that is attached to the ceiling by two cables. We're asked to calculate the tension in cable 1 in terms of the two angles, theta 1, theta 2, and the mass of the chandelier m. We'll go ahead and start off by drawing a free body diagram for the chandelier. So let's think about the forces that are acting on the chandelier. First, we have gravity, which always is directed straight down. And the way one calculates the force of gravity, also known as the weight of the chandelier, is one multiplies the mass of the chandelier times the free fall acceleration, negative 9.8 meters per second squared. And I'll go ahead and explicitly take into consideration the direction of that force with a negative sign out front. So the negative just means that the force is directed downward, and from here on out, g will represent the absolute value of the free fall acceleration, so positive 9.8 meters per second squared. Now, supporting the weight of the chandelier, we have the two cables, and cable 1 pulls towards the ceiling with a force T1. T stands for tension. And cable 2 pulls on the chandelier towards the ceiling like so, and it pulls with a force T2. Now, since cable 1 makes an angle of theta 1 with respect to the ceiling, we can say that the angle that T1 makes with the horizontal is also theta 1. Since those two angles are alternate interior angles, they have to have an equal measure. The same can be said about tension T2. So tension T2 makes an angle of theta 2 with respect to the horizontal, because cable 2 makes an angle of theta 2 with respect to the ceiling. Now that we have the free body diagram, we can go ahead and break up our forces into x and y components. Now, you'll notice that gravity is already pointing in the negative y direction, so that force does not need to be broken up. But T1 and T2 are pointing diagonally, which means that they are a mixture of x and y, so they will need to be broken up into components. So let's go ahead and break up T1 into components. Now, when you break a vector up into components, remember that the vector itself will always be the hypotenuse of the right triangle that you draw, and that the other two sides will be perpendicular to each other. So that's my x component, because that component's parallel to the x-axis, and this one's my y component, because that component's parallel to the y-axis. And this angle here is 90 degrees. So I've drawn a right triangle in order to break T1 up into its components. So the x component is adjacent to the theta 1 angle, so for adjacent, we'll use cosine. So I have T1 cosine of theta 1. And for the opposite side, I'll use sine. So I have T1 sine of theta 1. So I have the x and y components for vector T1. I'll do the same thing for vector T2. I'll draw the right triangle, with T2 being the hypotenuse. The x component is adjacent to the angle theta 2, so we'll go ahead and say that the x component is T2 cosine of theta 2. Remember that the adjacent side of a right triangle will always use the trig function cosine. All right, and the y component is opposite to the angle theta 2, so we'll go ahead and use the sine function for that one. So I have T2 times the sine of theta 2. So we can go ahead and draw a force table. So what is a force table? So I'll have an x and y column, and in the x column, I'll go ahead and put in all of the x components of all of the forces acting on the chandelier. So I have T2 cosine theta 2, that's an x component. I also have T1 cosine of theta 1, that's also an x component. My y components are t1 sine of theta 1, t2 sine of theta 2, and gravity, negative mg. Now, since the chandelier is in equilibrium, we know that it's not accelerating along the x direction, and it's also not accelerating in the y direction. So the acceleration in each direction is 0. So if we go ahead and apply Newton's second law, we have the summation of forces in the x direction equals mass times acceleration in the x direction. But since there's no acceleration in the x direction, from this equation, it follows that the summation of all the x forces equals 0. For the same reason, since the acceleration in the y direction is 0, the summation of all the forces in the y direction is also 0. So these are the equilibrium conditions. In order for the chandelier to be in equilibrium, these conditions have to be met. So this will give us two equations that will solve simultaneously as a system of equations in order to solve for the variables t1 and t2. So I'll go ahead and start off by summing the forces in the x direction and setting that sum equal to 0. So I have t1 cosine theta 1 plus a negative t2 cosine of theta 2, and that's going to equal 0. I can go ahead and add the t2 cosine theta 2 term over to the right side, which then leaves me with t1 cosine theta 1 is equal to t2 cosine theta 2. So I'll go ahead and box that equation, and I'll call it equation number 1. So the wide degree of freedom will also give me a direction. So I'll have the summation of forces in the y direction is equal to 0. Since the chandelier isn't falling, the acceleration in the y direction should be 0. So the sum of all the forces should be 0 in that direction. So I have t1 sine of theta 1 plus t2 sine of theta 2 plus negative gravity, mg, equals 0. I'll go ahead and add the mg over to the right side. So I'll have t1 sine of theta 1 plus t2 sine of theta 2 equals mg. So I'll go ahead and box that equation, and we'll call that equation 2. So we have a system of two linear equations in two variables. The simpler equation is equation number 1, so we'll go ahead and start with that one. I can solve equation number 1 for t1 in terms of t2, or alternatively, I can solve for t2 in terms of t1. Either way, we'll get to the correct result. So I'll go ahead and solve for t2 in terms of t1 by dividing both sides by cosine of theta 2. So that leaves us with t2 is equal to t1 multiplied by the ratio cosine of theta 1 divided by cosine of theta 2. So this isn't a third equation here. This is really just equation number 1 rewritten, such that I now have t2 solved for in terms of t1. So what I will do is I'll go ahead and substitute t2, the expression for t2, into equation number 2 in place of t2. So now I have t1 sine of theta 1 plus t2 is now replaced with t1 times cosine of theta 1 over cosine of theta 2. Can't forget about that sine of theta 2 term. So that's still there, so sine of theta 2. And that all equals mg. Now keep in mind, guys, that g here represents the absolute value of the free fall acceleration. So this is positive 9.8 meters per second squared. So I've effectively eliminated t2 from that equation, and I can actually factor out t1 since it's in common in both of the terms on the left. So I have t1 times the quantity sine of theta 1 plus cosine of theta 1 over cosine of theta 2 times the sine of theta 2 is equal to mg. Now, what I'll do is I'll go ahead and multiply both sides by cosine of theta 2. And if I distribute the cosine of theta 2 to both of these terms, I'll be left with t1 times sine of theta 1 cosine of theta 2 plus, in the second term, the cosine theta 2 cancels with the cosine of theta 2 in the denominator. So I'll be left with cosine of theta 1 times sine of theta 2. And the cosine of theta 2 term in the denominator was canceled out by the cosine of theta 2 term in the numerator. And then the right side of the equation is just mg times the cosine of theta 2. Now this is just a trig identity. So we're left with t1 times sine of theta 1 plus theta 2. So sine of theta 1 plus theta 2 is just equal to all of this. So sine of theta 1 times cosine of theta 2 plus cosine of theta 1 times sine of theta 2. You're probably more familiar with that trig identity with alpha and beta. So sine of alpha plus beta is just the sine of alpha, cosine of beta, plus the cosine of alpha times the sine of beta. And all of this equals mg times the cosine of theta 2. So you could go ahead and divide both sides by the sine of theta 1 plus theta 2. And the result is t1 is equal to mg cosine of theta 2 divided by the sine of theta 1 plus theta 2.